Hey, what's up guys? This is Dr. Vivek Palipuram and I'm bringing you the next lecturette in ECPE 127. This is lecturette 5 where I'm going to show you some problems using probability density function. Now in our previous lecturette, I introduced you to probability density function and we discussed why it is the most important probability model for a continuous random variable. If you have to find the probability that your continuous random variable x belongs to a given interval, all we have to do is just integrate the PDF over that interval. So let's solve some problems based on probability density function. So in this problem, first, I need to solve for the PDF and then I need to find the probability that y is in the interval 1/4 exclusive but 3/4 inclusive. So you can pause your video here and give it a fair shot on your own. And then once you're ready, you can unpause the video and I'll show you the solution. All right, guys. So this PD or CDF is equal to 0 for y less than 0. It's equal to y cubed between 0 to 1, and it is equal to 1 for y greater than 1. Now remember that the first derivative of the CDF gives you the PDF f of y. So all I need to do is differentiate this CDF. So I'll differentiate the CDF with respect to y to get f of y. So I differentiate d by dy 0 because that's the CDF for y less than 0. I differentiate y cubed because that's the CDF between 0 to 1. And I differentiate 1, which is the CDF for y greater than 1. And therefore, I get the PDF as 0 for y less than 0. It's equal to 3y squared for 0 to 1. And it is equal to 0 for y greater than 1. So the shape of the CDF now, or rather the PDF, is it's 0 for y less than 0, between 0 to 1. It takes a nice parabolic shape, and then it is 0 after that. Now, remember one thing about the PDF, guys. It doesn't matter whether the PDF goes up or down or what have you, as long as it is always above the x-axis or the horizontal axis. The reason is the CDF is a continuously increasing function of the random variable until it achieves the value equal to 1. Now, because the CDF is an increasing function of the random variable, its derivative is always going to be positive. So remember that your f of y has to be always positive, and it is not constrained that it has to be less than 1 or what have you. For example, in this case, the maximum value of the PDF is equal to 3. But we are never interested in the actual value of the CDF at any point. We are never interested in finding the probability that x is near a particular value. In this case, the value of the PDF is equal to 3 for y equal to 1. It just tells you, it gives you an indication as to what is the probability that y is near 1. Okay, so the next part that I have to solve for is the probability. So let's solve the probability part. I need to find the probability that y is greater than 1/4 but less than or equal to 3/4. So to get this, I will integrate the PDF from 1/4 to 3/4. Now I have to see which function or which part of the PDF I need to use. So the PDF is 3y squared between 0 to 1. The limits 1/4 to 3/4 belong to this particular interval. So I'm going to use 3y squared as my function for the PDF. So when I integrate this, I get y cubed, and the limits are 1/4 to 3/4. And therefore, I get 3/4 cubed minus 1/4 cubed as the probability. All right, so let's move on and solve problem 20.2. As before, you can pause your video and try to solve this problem on your own. All right, so let me give you the solution for this particular problem. The PDF, the probability density function, is a squared x times e to the negative a squared x squared over 2 for x greater than or greater than 0. It's equal to 0 otherwise. I need to find f of x. F of x is the CDF. Now, the f of x is obtained by integrating the PDF from -infinity to x. Now, from -infinity to 0, this particular PDF is actually 0. Notice that it is non-zero only for x greater than 0. So it is 0 from -infinity to 0. But from 0 to x, this PDF takes the form a squared x e to the negative a squared x squared over 2 dx. My apologies, guys, for the sound in the background. That's rice cooking in our nice pressure cooker. Okay, so let's solve this integral. Now, I'm going to show you a technique called integration by substitution. You must have seen this in your Calc 2. So what I'm going to do is declare a variable called v and set it to a squared x squared over 2. And then if I were to differentiate both sides with respect to x, I get 2a squared x. And therefore, dv is equal to 2a squared x dx. Now I can replace or 2. So these 2 and 2 get cancelled. So dv is equal to a squared x dx. Now I can replace a squared x dx with dv. And I can replace a squared x squared or 2 in each exponent as -v. Integral. Now, the limit of integration has to be found carefully. So when x is 0, so is v. Because if I were to substitute x as 0 here, v is equal to 0. So when x is 0, v is 0. But when x is x, v is a squared x squared over 2. So the limits are 0 to a squared x squared over 2. When I solve for this integral, I get negative e to the negative v, 0 to a squared x squared over 2. When I plug in a squared x squared over 2, I get negative e to the negative a squared x squared over 2. Minus, when I plug in a 0, I get a -1. Negative and negative make it a +1, minus e to the negative a squared x squared over 2. So f of x is 1 minus e to the negative a squared x squared over 2 for x greater than 0, because we were integrating the PDF for x is greater than 0. For x less than 0, it is equal to 0. Now notice here, if I were to substitute x as infinite here, the exponential term will rapidly plummet to 0. So f of x becomes 1 for x is equal to infinity. So it is indeed a valid PDF or valid CDF. When I plug in x is equal to 0, I get e to the negative 0. So e to the 0 is actually 1. So 1 minus 1 is equal to 0. So this CDF starts at 0, and then it climbs all the way to 1. Okay. Now let's solve problem 20.3. Here I have to find several items here. First, I need to get the CDF. So let me just divide the space into 4 quadrants like this. I need to get the CDF first and the probability that y is less than 1/2. F of y is equal to 3y squared over 2 for y between 0 to 1, and it is 0 otherwise. Let me ensure that this is indeed the PDF. Yeah. To get the CDF, capital F of y, I need to integrate the CDF from -infinity to y. And for this case, from -infinity to -1, the CDF is 0. But from -1 to y, the CDF is 3y squared over 2 dy. So I need to solve for this. So when I solve this integral, I get 3y cubed over 2 times 3. So 3 and 3 get cancelled out. And the limits are from -1 to y. So when I plug in a -1, I get, or when I plug in a y, I get y cubed over 2. And when I plug in a -1, I get -1 over 2. Negative and negative give me a positive. So 1/2 times y cubed over 2. Now this is the CDF for y between -1 to 1, and it is going to be equal to 1 for y greater than 1, and it is going to be equal to 0 for y less than 0. Okay, so that's the CDF. Now, to get the probability that y is less than or equal to 1/2, what I can do is just substitute 1/2 in the CDF. So I'll just substitute y is equal to 1/2 here. So I get 1/2 plus 1/16. So that gives me 9/16 as the probability. The next item that I need to find is the expected value of y. Now, expected value of y is an integral from -∞ to infinity y times f of y dy. So from -∞ to -1, this CDF is actually 0. So this CDF is non-zero, or this PDF is non-zero, only for -1 to 1. So y times 3y squared over 2 dy. So I need to integrate from -1 to 1, 3y cubed over 2 dy. So that gives me 3 over 8 y to the 4 from -1 to 1. When y is 1, it is 3 over 8. When y is -1, it's also 3 over 8. So the expected value is actually 0. So that's the expected value. Next, I need to get the second moment, which is y squared. So that's obtained by integrating from -∞ to infinity y squared times f of y dy. From -∞ to -1, this PDF is 0, but it is non-zero only for -1 to 1. So I have this form right here. When I perform this when I solve for it a little bit more, I get 3 over 10 y to the 5 from -1 to 1. When y is 1, it's equal to 3 over 10. When y is -1, it's -3 over 10, which gives me my second moment as 3 over 5. Now the variance of y is expected value of x squared. Well, in this case, expected value of y squared. It's expected value of y squared minus expected value of y whole squared. Okay, so variance of y is expected value of y squared, which is 3 over 5. Expected value of y was 0, so 0 squared, which gives me 3 over 5. And therefore, the standard deviation is square root of variance of y, which is square root of 3 over 5. So that's the complete solution for this problem. This was part A, this was part B, this was right here part C, and this one was part D. Okay, so that brings us to an end of a lecture covering probability density function theory and the expected value theory. Just like how you had multiple families of discrete random variables, you also have multiple interesting families of continuous random variables, such as uniform, exponential, Erlang, and there's one more guy, which is the most important one, the one that is found normally in nature, and that is your normal or the Gaussian distribution. These are the items that we'll cover in our next lecture. For your Friday's in-class participation, here's what I would like for you guys to do. For Friday, March 28th by 2 p.m. on Canvas, upload solution for this problem. Let's say that you have f of x, which is equal to lambda times e to the negative lambda x for x greater than or equal to 0, and it is 0 otherwise. What you need to do is give me expected value of x, give me variance of x. I would like for these two items from you. Please upload it on Canvas. All right, so that brings me to the end of this lecturette. Adios, guys.